A growing number of applications will benefit from working simultaneously in multiple frequency bands to improve system agility, configurability, and, in the end, performance. In this video, to demonstrate the feasibility of designing a powerful multiband transmitter, we will focus on the use case of a synthetic aperture radar or SAR imaging system. Indeed, radars have different capabilities at different frequency bands. Lower frequency bands like P, L, and C bands offer better performances on penetration depth and on targets detection. While with higher frequency bands like X, Ku, and Ka bands, it is easier to obtain accurate range and position measurements. So, there is a definite advantage in being able to develop a unique multiband SAR imaging system capable of generating signals in all these bands simultaneously. Especially now, with the availability of the latest Teledyne E2V dual-channel DAC EV12DD700, capable of direct signal generation up to 25 GHz at a sampling frequency of 12 gigasamples per second per channel. Now, let's look at the proposed multiband SAR transmitter architecture. Thanks to the high sampling frequency of 12 gigasamples per second, L and C bands are generated simultaneously in first Nyquist zone of DAC channel A using NRZ mode. And on DAC channel B, X and Ku band are generated simultaneously in second and third Nyquist zones using RF mode. Indeed, DAC EV12DD700 can configure a different mode on each channel. NRZ mode to maximize DAC output power in first Nyquist zone, and RF mode to optimize DAC output power in second and third Nyquist zones. Now, let's quickly detail transmitter frontend. At DAC outputs, multiple stages are necessary. Filters to select the desired bands and to remove unwanted aliased bands before to transmit the signal to the antenna. Power amplifiers to meet the transmitted power requirements on each frequency band. And wideband circulators to share the same antenna between transmitters and receivers. We have seen system architecture and frequency plan. Let's get to the demonstration. For this demo, we use one of our DAC EV12DD700 evaluation board, a signal generator to generate the 12 GHz DAC input clock, and a spectrum analyzer to monitor DAC output. With a graphical user interface, we can configure the DAC with NRZ mode on channel A and RF mode on channel B. We also use our integrated pattern generator to generate a multitones pattern in each band of interest. Here, a L-band pattern between 1 GHz and 1.5 GHz and a C-band pattern between 4.75 GHz and 5.5 GHz. Now we have generated the pattern, let's look at DAC output spectrum on channel A. We can see that L and C band are directly sampled in the first Nyquist zone between 0 and 6 GHz. Now let's generate a multitones pattern in X band and Ku band. X and Ku bands fold without overlap in the first Nyquist zone in the range of 1.8 to 3 GHz and 4 to 5.5 GHz respectively. Then, this pattern will be repeated in second and third Nyquist zones, and bands of interest can be selected using appropriate bandpass filters. This brings us to the end of this video. You have just seen how DAC EV12DD700 can help you to design a powerful transmitter capable of generating simultaneously multiple bands in different Nyquist zones from L to Ku band. If you want to start to evaluate the DAC EV12 DD700, or if you have questions on multiband signal generation, please contact us using Teledyne E2V hotline email address. Thanks for watching.